Hello everyone, this is the week 12 worksheet solutions. So for the question number 1, we're going to plot 3 points on polar coordinates on the Cartesian plane. Because we're using polar coordinates, we gotta remember that we are working with coordinates of the type r, theta. So the first entry is the radius of the circle that we're going to be working in, and theta is going to be the angle that we're managing. Now notice that because they all have radius equals 1 in this point, except for this one, which is minus 1, then we're going to use the circle of radius 1. This with minus 1 is going to have is going to make sense in a little bit. But what happens is that essentially we got to take a look at what are the angles. So for example, for 1 pi over 4, the first thing that I gotta do is I set the radius being 1, and once that I'm in the circle of radius 1, what I'm going to do is simply take a line at the angle pi over 4. So notice that pi half is here, so pi over 4 is kind of like in the middle, so pi over 4 will be this. And so this point that I'm reaching here, this will be the point 1 pi over 4. In a similar fashion, this will be 1 pi half. And so, of course, this will be 1 pi. And this one here is going to be 1 3 pi half. So now we're just going around the circle depending on the angle that we're using. Okay. So here's angle pi over 4. This is the theta that is running. Angle pi over 4. Here's angle pi half. Here angle pi. And here angle 3 pi half. Now what happens with the last point? This says that it's minus 1 pi half. Well, it turns out that what's going to happen is that we're still in the circle of radius 1. But we're going to be on the angle pi half. And so once that we get in the angle pi half, what the minus 1 is going to do is that it's going to reflect the point. So now, instead of being here, it's going to be here. So effectively, the point minus 1 pi half is equivalent to the point 1 3 pi half, because it's reflecting the value with respect to the axis. Now that we understand that we're going to do this way to describe the points, then it kind of makes sense to use a couple of examples. So let me show here with some different functions. So a function in terms of theta is always defined by r. R equals something. So when we're doing only the constant, we have a circle like what we had before. We can increase the radius of the circle, and that's just going to enlarge what the circle is, or compress if you want to. You can compress that out, or you can take a negative radius, and as you can see, it's the same thing, it's just flipping around the points. Now, if you take something like a curve, and for example here I have r equals to sine of 3 theta, or r equals cosine of theta, and I can define what are the directions that I'm picking. So for example here, if I only do it between 0 and pi half, notice that I'm getting just this piece. If I do just like pi over 6, I get this piece. And all this happens is because every time that I'm plugging one of the angles, this is giving me a value of the radius for that given angle. So I'm saying, oh, okay, so 0, angle 0. So with the radius is going to be 3. So I get this point. But then if I start moving and I say angle, I don't know, pi over 6, then I get all this movement in here between 0 and pi over 6. I get to make all this picture. Now if I do twice that and I do with pi over 3, notice that I draw this piece over here, And then I can continue doing that. Now I'm going to do pi over 4. And I'm going to do 2 pi over 3. And then you can see how I'm drawing all the pieces of this. If I just go up to pi, then this is going to completely fail. When a full turnaround, I'm completing this out. Of course, this is because we are going 3 times as fast because we have this 3 theta here. If I just have a theta, then this is going to work out very differently. If I move between 0 and 2 pi, or if I move here's just a circle there's being moved, but if I change how this behaves in here, then I have a different numbers of things that are happening. Okay, and similar thing can happen here for the r equals 2 sine of 3 theta. And so this is the way that the points are being constructed here. Okay. Now, a lot of what we can do with polar coordinates are very similar to the things that we do with normal functions. So, for example, if I'm going to change this area and find what is the total area here, I can do it with an integral. So the integral that gives me the area is the integral of r squared the theta. Okay, and of course I gotta check what is the possible angles that I'm going for. This here is a symmetric situation, and I can, if I'm not mistaken, this is 1/2 r squared. Yeah, 1/2 integral of r squared to theta, if I'm not mistaken, and this is going to go between 2 different angles that go here and here that are represented by this line here and this line here. So in particular, notice that I can just do this twice since it's symmetric. So I can just go and say, well, that's going to be equals to twice 2 by 1/2, and then I'm going to go and say, well, the maximum that we're going to go with this pedal is this line here, which is the pi over 6 line. And this is something that I can see, of course, graphically here, but you can kind of take a look of how much is going to take me to complete a full turn in here. And so this is 0 to pi over 6 of, and then the function is 3 cosine of 3 theta. So this is 9 cosine square of 3 theta, the theta. So that'll be, cancel this out, and this is 9 0 to pi over 6 of cosine square of 3 theta, the theta. Now to complete this integral, then I gotta use the double angle identity formula for cosine square. And so I can see this as 9 in this integral here. It can be replaced by 1 plus cosine of 6 theta over 2, and this over theta. Now at this point I can go ahead and split this integral. Of course, I can see it as 9/2 multiplying the integral 0 pi over 6 of the theta plus integral 0 pi over 6 of cosine of 6 theta. Now this is nine half, and this first part is just gonna give me pi over 6, and then this part, of course, is the integral of cosine is sine, so this is gonna be 1 over 6 sine of 6 theta, and this is gonna go between 0 and pi over 6. Of course, when we plug in here, that's going to be a 0. So this is 9/2 of pi half, pi over 6, sorry, plus 1/6. And then this is sine of pi, which is 0 again, when I plug in pi over 6. When we plug in pi over 6 with sine of 6 theta, it becomes sine of pi, which is also 0. And 0 is 0, so it's only going to be this 9 pi over 12. Okay, so that's the total area of this shaded rose petal here. Now, if we're gonna go and do the something like using the same function, which is r equals 3 cosine of 3 theta, and we're gonna establish the equation of the tangent line, there's a few things that I need to do. So the first thing is I need to establish what is the slope and the point, of course, because that's what I always need for an equation of the line. For m, the slope, of course, I'm going to need the y dx. And for x0, y0, I'm just going to need to find out what are the coordinates. But if you think about it, x is r cosine of theta from the translation to polar coordinates, and y is r sine of theta. So I can pretty much find out what that is by plugging in pi over 3. Notice that if I plug in pi over 3, I can find out that in theta equals pi over 3, we have that r is going to be 3 cosine of pi. So r is just going to be minus 1. Okay. And of course, then the point is going to be given by minus 1 cosine of pi over 3 and minus 1 sine of pi over 3. So that'll be the result of once that we calculate that, then we have the particular points that we need. So this is going to give me the point minus 1/2 and for the sine, then we're going to have square root of 3 over 2, or in this case, with the minus, it will be the point minus the square root of 3 over 2. So we already have the point. That's the initial part. Now, to find out what the y dx is, well, I have this polar coordinate function, so I need to work in terms of what is this in terms of theta. So the y d theta over the x d theta. That's what I need to find out. Of course, I have that information coming from here. So I can use this polar coordinate functions here, and then the y d theta, because this is a function in terms of theta, everything, and we can assume that r depends of theta because r is dependent of theta according to this. So there's a product rule going on in here. So we have the r d theta, sine of theta, plus r cosine of theta. That's the derivative of y. And now in terms of x, then we have the r d theta, and then the derivative of cosine is minus sine, so I'm going to have minus, oh, sorry, never mind. So this is the r d theta, and here we have cosine, and then now minus r sine of theta, according to product rule. Now I plug in pi over 3 again, so to get my point, so m is the y dx at pi over 3. Oh, by the way, I need to find out what the r d theta is, but the r d theta is just a derivative of r with respect to theta, and that can be simplify here. So if I take the derivative of cosine, of course I'm going to get sine, and I get chain rule here, and this is going to give me a 3 here. So this is minus 9 sine of 3 theta. That's what the r d theta is. And so this by sine of theta plus r cosine of theta. And I replace also that here. Minus, minus. And now I get to see what this is once that theta is equals pi over 3. So I just need to plug in every single one of this. So this is minus sine, minus 9 sine of pi over 3 is just going to give me a pi here. And of course this is minus 1 cosine of pi over 3. And then again minus 9 sine of pi cosine of pi over 3. And then minus 1 sine of pi over 3. So this goes away because sine of pi of 0. So this is just going to lead me to whatever this is. And so this is going to be again minus 1/2 over, and this is going to be positive now, but sine of pi over 3 is the square root of 3 over 2. And so this is essentially minus 1 over square root of 3. And so that's going to be my slope. So now I have a slope and point. I have everything that I need for my equation of the line, which is y minus y0 equals m x minus x0, or y plus square root of 3 over 2 is equals to minus 1 over square root of 3 x plus 1/2. And so this here is the equation of the line. Now last for question number 4, we want to sketch the curve r equals 2 sine of 3 theta and find the area that encloses. So the area, the graph of r equals 2 sine of 3 theta can be found in multiple ways. You use a graphing calculator or Desmos and you can do that. You're gonna get something like this. It's a flower with 3 petals. And as you can see here, from the overlay from the angles, we can pretty much are going from 0 to pi over 3 to cover the full petal. So if we are going to calculate the area, by symmetry we just need to calculate one of the petals. So we can do a equals 1/2 0 to pi over 3 of r square of theta d theta. But then again, this is the function 2 sine of 3 theta square, and so that's going to give me 1/2 times 4 integral from 0 to pi over 3 of sine square of 3 theta. And then again we do the same trick that we did before. We use the double angle identity for converting this square into something much more simple, and this is going to be 0 to pi over 3, and this is going to be 1 minus, and then is going to be sine of, if I'm converting sine square into cosine, this is going to be 1 minus cosine of 2 theta of 2 times 3 theta, so this becomes 6 theta over 2 divided by 2. And so the two are going to cancel each other, and this is going to be the integral from 0 to pi over 3 of the theta plus, or actually minus, the integral from 0 to pi over 3 of cosine of 6 theta. Now notice the two cancel each other here, and so if I integrate the theta, it's going to be theta, and between pi over 3 and 0 is just going to be pi over 3. And now for the integral of cosine is of course going to be sine. And so this is going to be minus sine of 6 theta over 6 in between 0 and pi over 3. Of course, when this is 0, then this is 0. And when this is pi half, then this is going to be 1. So this is pi over 3 minus sine. And sine of 2 pi is also 0. So this at the end is just pi over 3. Now this is just a single petal. So if I'm doing the 3 petals, then I gotta multiply the whole thing for 3. This is the area of a petal. So the total area is 3 times the area of a petal. And it's 3 times pi over 3. So this is just gonna be pi. So the whole thing has area pi. And that is the end of week 12's worksheet solutions.